So now we want to welcome MJ Johnson, who is a NASA Solar System Ambassador. He's come down from Shrewsbury for us tonight to do this presentation, and we're very excited. Thank you, MJ.
My son is much more technical than I am, and so he's asked if I can try and solve this problem of getting full screen. I will do my best by pressing. Aha! See, your old man does know how to do a couple things. All right, my name is MJ Johnson, and as Jean just said, I have the privilege of being able to go around and give talks like this one we're going to hear about here tonight. And thank you all for being here on a Friday night. It's so exciting for me always to be in a room filled with people who show up for these kinds of talks, because I'm assuming that means that you have interest in the same kinds of things that I have interest in space science and what we as a human society are trying to do to learn more about that which we know a little bit, because the amazing thing is there's so much to learn, and tools like the James Webb Space Telescope, which will be the primary thing I share with you this evening, what it's doing to help us answer questions that we've had for as long as we've been looking up at the skies, and giving us a whole new category of questions to ask that we're just beginning to understand even how to begin to ask them. As Jean said, thank you very much to the South Shore Astronomical Society. Thank you so much for your support and for bringing the telescopes here out tonight. And then, of course, thank you to Jean and to the Scituate Historical Society for the opportunity to share with you guys everything that I'm about to share. I did try, I figured there would be a question about, like, well, how do we go? If you do have your cell phones and you want to take a picture, there it is. That's how we get to the Lawson Tower. So there's your straight up to the light, you make the right, and you go the 0.2 miles, and you make the left, and you'll see Lawson Tower up there on the left-hand side. So that's what hopefully we'll have a chance to do after this presentation. So as Jean sort of mentioned, if you do have interest in space science, as I have for many years, I became aware of this program, the Solar System Ambassadors Program. It is a citizen education, society where people that have interest in these kinds of topics get to go around and share with local community groups, libraries, scout troops, historical societies. It is run by the Jet Propulsion Laboratory out of Pasadena, and they are once a year in September. If you are interested, you can apply to become a Solar System Ambassador. I will say one of the coolest things about the job is you get the opportunity not only to do presentations like this one, but they do training regularly. They do webinars, and you get to hear, from my opinion, incredibly, from the actual mission primary and principal investigators and people who are actually at NASA doing the science which you will learn about tonight. I always figure they have something better to do than to talk to me, but I'm grateful for them spending time, because it really is always fascinating, and then I try and take what I've learned and carry it out to folks like yourselves on events and evenings like this evening. So I am going to speak mostly about the James Webb Space Telescope this evening. I'm going to guess, like, how many people have heard of the James Webb Space Telescope? Okay, right, awesome, fantastic. So this is actually, I went looking for some pictures that I thought were a little bit unusual. This was a full-scale mock-up of the James Webb Space Telescope, which they put on display at the South by Southwest Festival in Austin, Texas in 2005, I believe is when they did this. But it does give you a little bit of a sense of the size of it. It's quite large. It's about the size of a tennis court when it's fully deployed. And that mirror up there, which you can see is extremely large, about 18 feet across, is the largest telescope mirror, certainly to be deployed in space, and we'll talk about why they did that. My talk will primarily be in three different sections. I'll talk first of all a little bit about the history and the road leading up to the Space Telescope. I'll talk a little bit about what the engineering considerations were when they were building it, and then I'll talk a little bit about some of the science that the Webb was built for and what it's helping us to understand. Before I go into that, I can't help myself. There's always so many things to talk about from a space science perspective. So if you'll indulge me for just one moment, there's something very exciting I need everybody in this room to know, if you aren't already aware. In just about 50 days from now, there will be a total solar eclipse that with the path of totality, which I will talk about what that is in a moment, is very close to us right here. You can travel just slightly west of us into New York, or slightly north up into Vermont or into Maine, and you can be in the path of totality. And I will share with you that in the 20th century, in North America, we did not have very many total solar eclipses. We had partial solar eclipses, and maybe many of you have seen them. That's when, if you looked, because you're never supposed to look directly at the sun, but if you looked at a projection of the sun, you would see, it looks like it's kind of got the cookie bite out of the cookie, right? So you got the disk of the sun, and then you've got that crescent shape that comes out of it. That's what you see in the top row here. That's a partial solar eclipse. Does anybody know, like, in terms of what is happening during this event? And maybe I'll ask some of the younger members of our audience. What's a solar eclipse? Does anybody want to try and describe it? Do I have a volunteer? Go ahead.
Basically, it's when the moon gets in the way of the sun, and it causes the shadow of the moon to block the sun's light for a short amount of time.
That is a perfect explanation. What's your name, sir?
Matthew?
Matthew, thank you so much. That was an amazing description of exactly what happens during a solar eclipse. Now, when a solar eclipse happens, that is everything you just described, 100% accurate. During a total solar eclipse, there is this incredibly, seemingly unique fluke of geometry which comes into play, which is the size and the distance of the sun and the size and the distance of the moon are from the Earth just about the same size, which is seemingly really unusually rare, but is in fact geometrically accurate. And so during a total solar eclipse, the disk of the moon completely covers the disk of the sun. And when that happens, some very unusual for our usual daytime experiences happen to us. And so, first of all, it gets very dark. I had the opportunity to observe my very first total solar eclipse during the last North American total solar eclipse in 2017. And it sort of becomes like a twilight light. The light is really kind of spooky and weird. And you see these very strange things coming out from the sun. Does anybody know what that is? My buddy Matthew, what is it?
The sun's corona.
The sun's corona. What's the sun's corona?
Basically, a layer of gas that is around the sun.
Yes, it's basically the atmosphere of the sun. So it stretches very far beyond the surface of the sun and is normally totally, completely invisible to us. It is only when the sun is covered by the disk of the moon during a total solar eclipse that we're able to see the corona of the sun. It is a beautiful, ethereal thing to witness. I encourage all of you to seize on the opportunity if you are able. This is the path of totality. If you look at that shadow right in the middle there, that is the only part of the United States that you can be in and observe what I just described. And so as you move into New England, in northern New England, you can see that it will pass the shadow of the sun, as Matthew just described, will pass directly over western New York and into Vermont and up into Maine, not very far from us. And you may want to know more about that, and that's why I put the website that I took these pictures from, eclipse2024.org. And on that website, they make it very easy for you to click on a part of the map, and it will tell you what the nearest town is. And if you click it a little bit further, it will actually give you a little animation of that's what that top picture is up at the top. It shows you a little simulated animation of what you might see if you were at that part of North America. It also contains very useful information like what time the moment of the total solar eclipse will happen and how long that will happen for. It will happen for about 4 minutes, depending on where you are during the center line of that totality. And then I also wanted to highlight this other, from this website, if you remember, eclipse2024.org, this other link here for Javier Hubier's interactive map, super cool resource. It will actually show you at any point in time what the totality of the shadow of the sun will look like projected onto the map. and you can click literally anywhere on this map. It'll give you all the information you need to know about what time will the eclipse begin and how long will the eclipse be. If you are towards the edges, you will have a shorter eclipse because, as you can see, the shadow of the moon, which is a disk, will pass over that part of the Earth more quickly than if you were on what's called the center line. Okay? So these are all resources that are available to you. I'm not associated with them, but they're useful pieces of information which I encourage you to check out. And if you do have the opportunity, please consider getting yourselves into the path of totality. It is very different from a partial solar eclipse, which is what you will observe from anything outside of that path of totality. And then I can't help myself, I have to mention this little guy here. It looks very well done for me. Thank you for the applause. For those who may not know, sir, would you care to share with the audience? Do you know what this instrument is?
Yeah, that is the helicopter that was on the latest Mars rover. It just shut down because its wing got damaged.
It did.
But it has given us great science and perception on different areas in that crater where the rover needs to go.
Absolutely. So this was this little device, and actually, in actuality, it's probably about this high, this big, it's about that large, and it was the first instrument to achieve powered flight not on this planet, anywhere, not on Earth. And it is designed like a dual rotor helicopter. It is actually what it is. It was designed and it hitched a ride on the Mars 2020 rover, which is one of the rovers where JPL and NASA are currently operating on Mars. And it was designed as a technology event test. It was really like, can we do this? It turns out it's really, really hard to achieve powered flight on Mars. Does anyone want to guess why?
The atmosphere is so thin.
The atmosphere is so thin. It's so thin that you need to get a pair of rotors moving really fast, like 3,000 times a minute, like very, very fast. But you can't get them going so fast that you start to create so much disturbance and all sorts of turbulence in the atmosphere that you no longer can sustain flight. So it was designed initially as a tech evaluation. The name of the helicopter was named by a student. It's called Ingenuity. And Ingenuity, the test of it was 5 flights. And it had a period between April and May where it was going to try and do 5 flights. And it nailed those in the first 3 weeks of its landing. It landed in February of 2021. It was deployed in April. And by the first week of May, it had achieved those first flights. It went on to fly 72 times. It flew 72 times. It flew over 2 years. It has changed. During the course of its deployment, it changed from can we do this to an actual integral part of the Mars mission, which we were just describing. So this idea now that we have proven that this can be done, I believe this has changed forever how we will do exploration in environments where there is an atmosphere where we can achieve powered flight, because literally this little guy was up in the air surveying the land before the rover even got there, and it was trying to determine what is a safe way to go or what is a place of scientific interest. It really was capable of doing that kind of scouting and then communicating that back to NASA so that they could make decisions about how they were going to move the rover forward. And so if you'll allow me, I'll just show a quick video on
and liftoff, launching the next generation of robotic explorers to the Red Planet.
We made it through launch, cruise, all of that, and we were ready now to begin our real mission, our real life on Mars. And we were all excited to see what Ingenuity could really do. We were ready for flight 1.
Earlier today, Ingenuity should have autonomously performed its first flight attempt on Mars.
And we're all holding our breath.
Ingenuity reporting. Altimeter data confirmed. Ingenuity has reported 3 flights on a powered aircraft.
So at that point, you just open the floodgates of what is possible.
Yeah, it was surreal.
That was the crowning achievement of the team.
You know, you really had to hold hands and do it together.
From that moment forward, really, we were off to the races and saying, okay, great, that's done, let's get back to work, let's get to flight 2, and then 3, and then so on and so on. How fast can we fly? How high up above the surface can we fly? We started doing things in parallel with the rover, and we've also demonstrated that the helicopter can be a scout to help scientists. journey. I think I highlight a couple of our lives to have been a part of it.
Of course, there's a little sadness that, oh no, it's over. It's kind of the end of an era, but it's also the beginning of an era.
To realize, what you're part of here, at least for me, I kind of get goosebumps.
We hope that ingenuity will inspire teams to build larger, more capable vehicles. From a science perspective, what is interesting now that we've unlocked that aerial dimension?
The best way to predict the future is to create it.
So yes, sad that Ingenuity's mission is done, but it really has, as they described, unlocked what is capable, what can be achieved, especially specifically in tandem with these two kinds of instruments and exploring other planets. So on to space telescopes. So I would invite anybody in this room to say, what is this image of? Anyone? Saturn. This is Saturn. Okay, that's great. We all know, like, Saturn and its uniqueness with its rings, but we didn't always know that. We didn't always know that Saturn had those rings. We used to just actually think it was a really weird star because it didn't move like the other stars. Who can tell me what type of object, if not the specific object, that this is?
Andromeda?
It's the Andromeda Galaxy. This is a galaxy. This is a collection of hundreds of billions of stars. Looks very much the way we believe our own galaxy looks like. And also, I will say the brightest object that can be perceived with the naked eye from the furthest distance, 2 million-ish light years away. And then the last one I'll ask in this series of what are these? Anybody know what this is an image of?
Eagle Nebula?
It is within the Eagle Nebula. It's actually, these are the pillars of creation, actually within the Horsehead Nebula, I believe. Is anyone correct? Yeah, so it's in the Horsehead Nebula, which is in Orion. It's in the Orion Nebula. All three of these things share something in common. What do you think I might be going for with this?
Star formation? Photos by JWST.
Photos by, so these actually photos were not taken by JWST, these were by Hubble. But actually what I was going for is that no one really knew any of these things before the invention of this guy right here. So before telescopes, we didn't really know very much about what things really looked like beyond the fact that they were very small dark dots of light. We could see them at night, and then we could kind of have some sense of them. We knew there was some differences between them. When you look at the Andromeda Galaxy, it has some nebulosity associated with it, and it's kind of hazy. Same thing with the Orion Nebula. The planets behaved weird, but they kind of looked like stars. But they really, what we began to understand about the reality beyond our own planet was really due to this guy right here and his invention. Anybody happen to know who this guy is? This is Galileo. So Galileo was the first human to put together some lenses in a tube and look through them. And one of the first things he started looking at and he started documenting was Jupiter. And what he noticed about when he looked at Jupiter was that it wasn't just one dot of light. It actually was multiple dots of light, and those dots of light moved relative to one another even over the course of a few hours. And so this is from Galileo's early sketchbook where he was trying to document what he was seeing when he was looking through the telescope and observing what ultimately turned out to be the brightest moons of Jupiter. They are now known, as they are named after Galileo, they're the Galilean moons. So this was the first evidence that we had that there were not just stars, but celestial objects that had their own orbital mechanics. They had their own components. They had their own little sets of worlds surrounding them. That was all because of the invention of the telescope. And I say that because we take so much for granted now. And it wasn't that long ago, just a few hundred years ago, where we had no sense beyond what we could see with our naked eyes of what these objects ultimately were. So fast forward hundreds of years and tremendous progress in terms of optics and lenses, and we have amazing ground-based telescopes, and we can see all kinds of nebula and galaxies, we can see clusters and galaxies, all kinds of things which we couldn't have even dreamed of. But through all of that, there was a little bit of an amazing thing in that it sustains life and allows us all to be here in this room tonight, which is here photographed in this image. Anybody know what I'm going for here? The atmosphere. The atmosphere of the Earth is miraculous because it allows life to be sustained here, but it's a little bit of a problem if what you really want to do is look at stars and planets and galaxies and everything else. And I tried to get a video here of what typically scientists and astronomers, backyard astronomers, like myself, see when they look through their telescope. They experience, when they point it at a planet or a star or anything that should be a solid point of light, they experience this kind of wobbliness to that object, which is referred to as scintillation. It is the movement of the atmosphere which prevents the light from reaching our eyes or our telescopes, our instruments, in a straight line, right? Because light is coming to the Earth, and then it comes and it hits the atmosphere, and as soon as it starts to hit that atmosphere, it's like when light passes through water, for instance, right? It refracts a little bit. So the atmosphere does all kinds of wacky things that make it a little bit challenging. This is actually another little animation. If we're looking at, as we hopefully will have the opportunity tonight to turn our telescopes towards the moon, it's amazing. You can see these craters and valleys and mountains and everything, but you can't get around the atmosphere as long as you're here on Earth. So scientists have known about this problem for some time, and so the good news is that scientists have been thinking about this for quite some time. This gentleman here, Dr. Oberith, he was I like this because it's just kind of cool. He's a Transylvanian Saxon physicist and engineer. I don't believe that he has any relationship to our man Dracula, but he's one of the founding fathers of rocketry and astronautics. And he, in 1923, proposed that a rocket could potentially propel a telescope into orbit around the Earth. Many years later, this gentleman here, Dr. Spitzer, there's now a space telescope named after him, American theoretical physicist, astronomer, and also mountaineer. He carried out research into star formation and plasma physics, a whole bunch of amazing things. In 1946, he conceived of the idea of telescopes operating in outer space, not just putting on a rocket and getting them higher into the atmosphere, but actually parking it in orbit outside of the Earth's atmosphere. And so then, as we progress, through the 20th century, we have the formation of NASA in the 1950s. We have the Apollo moon missions and everything that came before that, the Mercury missions, the Gemini missions, all of that science going into that. There were still many astronomers and scientists here on Earth that were wondering, okay, with all these newfound capabilities and all these new dollars that were flowing into space science, could we now conceive of a telescope that actually we could build and actually put into space? So in 1969, the Large Space Telescope actually was formalized as a NASA program. And then through the 1970s, mid-1970s, almost into 1980, this is actually the time when things started getting good. There was a working group that was formed, the congressional funding actually came into place. They started building the thing, and astronaut training also became a part of this as well. And all of this was, in many ways, developed hand in hand with the shuttle program. And I'll describe what I mean by that in just one second, because of course we need to be able to carry the telescope into space, we need to be able to deploy it there, and the way that the Hubble ultimately, I gave away the punchline there, but the way that it was designed was to try and make it so that it could actually gain new capabilities over time, and it could be serviced. And the idea was we could actually use this thing as a platform for continuing to do science over a period of time. So, of course, eventually the Large Space Telescope, as we just said, it was named, did get a name. It was named after this gentleman here, Edwin Hubble. This was a scientist, American astronomer, who played a key role in many aspects of what we now understand about astronomy, including the fact that Hubble was the first person to suggest that these blobs of haziness, we just saw the Andromeda galaxy, that they actually might not be part of our own galaxy, but they actually might be galaxies beyond our own. And of course he was right. There are certainly objects within our galaxy which are clusters, and they're contained within our galaxy. He was really the first one to see some of these objects and correctly evaluate them as island universes, other galaxies beyond our own universe. And of course, his name was given to the Hubble Space Telescope. And so this is just a very brief timeline that gives you a sense, going all the way back to the mid-80s. Let's see, 1990 was when Hubble was launched. When Hubble was launched, for those of us who were paying attention back then, it was a little bit of a disappointment. Does anybody know why?
It
didn't see so good. So the Hubble, as originally deployed, needed glasses. So the curvature of the mirror that was ground was not exactly what it needed to be for a variety of reasons. But because it was parked in relatively accessible orbit, it was launched into space on a space shuttle. I say that the shuttle program kind of evolved hand in hand with the Hubble because they really literally filled the entire cargo bay of the shuttle with the space telescope. It was almost custom built to fit in that space. It was the largest instrument that really could have fit into that space in order to loft it with the space shuttle. So when it was launched and it discovered that there was an aberration to the mirror, there was immediately an evaluation of what it would take to actually get it serviced, to get it operating as was expected, and then a subsequent mission by the Discovery, my favorite personal space shuttle, was launched in service of correcting the lenses, and they were able to put a corrective lens on the Hubble, and things have been truly astounding and spectacular since then. I would actually argue that the Hubble has done more to further space science than any single other instrument, certainly in the 20th century. So since then, that was why that picture that we saw, even if you didn't know that there was the Pillars of Creation in the Horsehead Nebula, many of you probably saw that image and recognized it as a Hubble image because it is one of the most iconic images. It has completely changed our understanding and our ability to see what resides in these very distant places in space. It was so successful, in fact, that we now actually have an entire constellation of space-based telescopes, many of which are observing in all different kinds of spectra of light. And that will lead us very soon now into the James Webb Space Telescope and what it is designed to do. So these are all, Spitzer I mentioned was that's an X-ray telescope, which is named after the scientist who gave rise to this idea of putting a telescope into space. But there are many, many others. Swift and Chandra, Kepler there's actually stickers back there for the Kepler mission. That's a space-based telescope. Its whole mission was to find planets outside of our own solar system. Very, very relevant for one of the missions that the James Webb Space Telescope is now executing. And I would say that truly, after Hubble launched, there were a couple different key moments in what Hubble was investigating that really gave rise to the idea of what eventually would be the James Webb Space Telescope. And I would say that the deep field images that Hubble imaged through the 90s and into the 2000s really were sort of the opening up I don't call it Pandora's box, but the possibility of what a successor to the Hubble might actually do. And so the deep field images were really just a series, and there were a few different ones of them, but the first Hubble deep field was an attempt by scientists to say, we don't know what we might find if we look at an incredibly otherwise uninteresting part of the sky and just stare at it using our state-of-the-art optics in the Hubble Space Telescope. And that was exactly what they did. They pointed the space telescope at a very uninteresting, no stars, no galaxies, nothing really that we would expect to be able to find. And what they found, after looking at it, was a piece of sky that looked like this, even to the Hubble, with a relatively short exposure. When you stared at it for about 2 weeks, actually I guess 10 days, you suddenly saw a whole lot more things than they were expecting to see. And what we started to realize was that there were many, many, many more distant objects and galaxies than we really could even conceive of. The idea that the original, I guess in the ultra deep field, as I said, there were multiple deep field images. In the Hubble ultra deep field in 1993, after that lens correction took place, it was a 10-day exposure. It just stared at this tiny little uninteresting patch of sky, and it discovered about 3,000 galaxies in this incredibly tiny little space. Matthew, do you have a question?
The reason it appeared after 2 weeks is because that was probably like very early into the universe, like very far away from us.
You're you're on the right track there. The reason why is the amount of light is so little. Like light is transmitted to us in these, it's a wave, it's a particle, it's these photons, right? The number of photons that are reaching us from these extremely distant objects are very few. Very few. They travel very far distances, and there's just not a lot of light that reaches us. So we really have to have very sensitive instruments that can be very precise in how they stare at a part of the sky for so long. But that is exactly why we suddenly could see these images. And so with that as the basis of the idea, Hubble was really born. I do have an image. You know what? Actually, if we have time at the end, I'm happy to go through this. This goes through a little bit about the ultra deep field. realize that a photograph that we're looking at from here on Earth really is comprised of many, many layers of different objects at different distances from us. And you start to get a sense, going all the way back to as far as we can see, exactly how far the furthest, truly furthest objects are from us in terms of how we interact with them. So then I will move on to this, which really is, that really did in many ways give rise to the idea of what we ultimately came to realize was important about Hubble. Important about the Hubble images that gave rise to the James Webb Space Telescope, that there's a lot more out there that we need to see. Now, one thing I do want to mention is, and as this animation, I'll just play that one more time, there is a concept in astronomy and in space science that as objects are further from us, and in fact as they are receding from us, one of the things that Hubble himself, Edwin Hubble, evaluated was that the galaxies are all receding from one another, that they're moving apart. And so when objects move away from one another, the light that comprises those objects that are reaching us is also stretched out. We experience this here on Earth as you know, when a car or a train goes by, and you have that sensation of as the train is on its horn approaching you, those sound waves are compressing. They're getting shorter, and so you hear that, and then it goes by. That's literally those sound waves that are compressing towards you as it's approaching you, and then as it recedes, those sound waves are stretched out. And light behaves that same way. And so what you start to realize is extremely distant objects, and also the ones that are furthest from us, experience this effect most dramatically. That as they're further and further away from us, and as Hubble predicted and evaluated, as they're receding from us, the light stretches from its normal wavelength into a redder wavelength. Red is a longer wavelength, and then the blues and the ultraviolets are the brighter wavelengths. And so what that means is, when you look at objects, let's see here. So when you look at objects which would have normally existed in normal visible spectra, which is how one of the key spectra that stars and galaxies and everything we can see with our naked eyes exists in the night sky, that as they're moving away from us, especially the most distant ones, they very much shift into this part of the light spectrum which we are not really equipped to see. We don't see infrared emitting, we don't see infrared light. We see visible light. We can experience infrared light as heat, but we can't perceive it with our eyes. And so the Hubble, as an example, I mentioned all those different telescopes, they're all designed to see in slightly different wavelengths. And so each of these different instruments that are in orbit as space telescopes around the Earth, they all observe, this is roughly how each of those scopes see in these different spectra, they all see objects in slightly different spectra. Now, if you're interested in seeing the objects, and they're optimized to see different objects. So some objects are designed, some of these are designed to see very powerful, very bright events. So we talk about, the matter which is swirling around black holes. That becomes extremely, extremely active, very hot. Those are very short wavelengths. That's when you want to observe in gamma ray and X-ray. So if you want to see, exploding stars, gamma rays and X-rays are your ticket. But if you want to see things that are very, very distant from us, especially ones that are receding from us, that's when you want to start to see in that everything to the right of visible, infrared, microwave, and even radio waves. Now, as I've already mentioned, we know that the atmosphere is kind of distorting the visible light rays. We talked about the effect of scintillation, but not only does it affect what we're trying to observe in visible light, different spectra are actually absorbed by the atmosphere. Again, under normal circumstances, this is very good. It means we aren't constantly being bombarded by X-rays and gamma rays, which are not very healthy for us if we were just constantly experiencing them here on Earth. But visible light does reach us. A little bit of that scintillation happens. Infrared and ultraviolet, those are not very well represented here at the surface of the planet. And then radio waves, we do actually have radio telescopes here on Earth. We can observe some of those. But the point is, the atmosphere is very good at filtering out things that can not be very life-sustaining, but very bad if you want to observe objects in any of those spectra. And that was really what gave rise to the idea of the James Webb Space Telescope.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. Some cosmic purpose, then let us find ourselves a worthy goal.
So of course that video features the voice of Dr. Carl Sagan, and it was designed to get people very, very excited about the mission of James Webb Space Telescope before it took off. James Webb Space Telescope is very expensive, and has returned already in just the very few years it has been operating more than what we have invested in it, and I can describe in many reasons why I believe that to be true. But it was expensive because what we set out to do is incredibly hard. Very much harder than what we had achieved with the Hubble. So what were some of the things that the engineers who designed the James Webb Space Telescope needed to overcome? First of all, they had to deal with temperature. Temperature in space is very, very difficult to deal with under any circumstances because space is by default extremely cold, except when there is sun shining on you, and then it is extremely hot because there's no atmosphere to regulate that. So this is why when astronauts went to the moon, when they were inside of the command module, that command module was constantly rotating because they never wanted to have one side baking in the many hundred degrees of the sun, while the other side is extremely cold, many degrees colder than freezing. So you constantly were rotating it because they were trying to maintain an even temperature on the hull of the ship. Those are one of the challenges that you have to deal with in space. When you're dealing with infrared, it's even harder because if you're, as I already mentioned, we experience infrared typically as radiation, like when you're warming yourself by the fire. That's a lot of infrared radiation which is coming off of that fire. We don't see the light, but we do experience the heat. And if you're trying to observe something in infrared, everything has to be really, really cold. So you need to be able to maintain the temperature. The distance was going to be a problem for a variety of reasons. I already mentioned Hubble was able to operate in low Earth orbit. We were able to pop up there when it didn't have the glasses it needed and give it new glasses. James Webb Space Telescope, for a variety of reasons, we didn't have that luxury. I'll describe why in a second. And then just the overall operations of it, being able to service it, it needed to be effectively a one-way trip. So let's talk about each of these things with James Webb Space Telescope. So this was one of the first challenges that they knew they were going to. We knew that we wanted to observe in infrared. We wanted to observe these extremely distant objects which are receding from us. Those appear most readily to us in infrared. But if you're observing in infrared, you have to make sure that your instruments that are observing in infrared are operating at nearly absolute zero. That is negative 233 degrees Celsius, negative 388 degrees Fahrenheit. Very, very, very cold. That is the atmosphere of space. That is the vacuum of space, effectively, that they need to be able to operate on. What they needed to be able to do was to create an environment where the other side was able to deal with the sun. And the sun is radiating light and heat and creating an environment which is as much as 185 degrees Fahrenheit. So you have this extreme condition where the part that is, effectively facing the sun and ideally getting some sort of power from that is able to keep the instrument side of the telescope at a very, very cold temperature. And the technology that they came up to deal with this is this incredibly innovative heat shield, which is actually comprised of multiple layers. And the reason why it's comprised of multiple layers is, you can see illustrated here, you have this one environment, you need gold, the other one, accommodate very, very hot. With each of these layers, because there is space and distance between them, they're able to dissipate more and more heat as you go through each one of these layers. These layers are incredibly large. As I said, the size of the telescope is about the size of a tennis court, but these are almost like the Mylar balloons you might get at a Target store. They're incredibly thin. We'll talk about why in a second, but spoiler alert, every pound counts when you're launching something into space. So you need a very robust system that's capable of dissipating heat, but that doesn't weigh very much. And you need to be able to fold it up all origami style so that it can fit inside of a rocket that you're then going to send off into space. So this was the incredibly innovative heat shield that the engineers working on Webb came up with. I believe I have, so this is just to give you a little bit of a sense. So you can see the heat shield, the size of that thing. There's a person for reference down below. You can also get a sense both of the size of the James Webb Space Telescope on the left and the Hubble on the right. You also get a sense of the main objective, the mirror that was used in the Hubble, and how much larger that mirror is for the James Webb Space Telescope. And I assure you, after what we went through with Hubble, they were working really, really hard to make sure that the precision on that mirror was going to be accurate. And as I already mentioned, one of the other key challenges associated with that very large instrument that I just showed you, which has that incredibly large objective mirror, the secondary mirror, it's got the heat shield, it's got all these very complex components, all of that needed to go in one of these, into an Ariane 4 or 5 rocket, and then get folded up origami style in order to be launched. So there was a fair amount of engineering just to figure out, okay, we figured out heat shield, we know what the primary mirror is going to be, how is this thing, not only does this thing need to be able to fold up and fit inside of this thing, that once they got it into space, it needed to be able to deploy itself completely autonomously. Yes, we could monitor it. Yes, we could make sure it was checking each one of the steps along the way, but it had something like 350 critical breakpoints. Any one of those points failed, any one of those failure points, the mission was over. So every single one of those 350 individual mission critical breakpoints had to go exactly according to plan in order for this thing to be in a condition where it could actually begin doing scientific operations. 344 points of failure. I don't know if I need to show the whole video. Let's see how long this guy is. It's about a minute, 44 seconds. This is what the thing looks like when it actually is going through each of its deployment stages. Webb to get parked. So this is a diagram, not to scale, but of the sun, the earth, and the moon relative to one another, the interplay of these sources of gravity, the sun, the moon, and the earth, each create natural places of gravitational stability in and around them. And they're in fixed places relative to the earth and to the moon and to the sun. These are known as Lagrange points. And so each one of these, L1, L2, L4, L5, and L3, these are places where, gravitationally speaking, you can park something, and due to the interaction of gravity between the earth, the sun, and the moon, they will pretty much stay there. And so these were the candidates that scientists started to look at in terms of where they wanted to be able to park the Webb Space Telescope so that they wouldn't have to have a rocket constantly spending fuel, energy, effort, restabilizing itself. Like when you orbit around the Earth, you have a stable orbit around the Earth, you're pretty much assured it will stay in that stable orbit around the Earth. We knew that Webb couldn't be close to the Earth. Does anybody guess why we couldn't be so close to the Earth? Like, why did we have to go into deep space with Webb? Cold? Because of the temperature. So Earth radiates enough heat that we wouldn't be able to operate the Webb Space Telescope in a way that would allow us to observe into the infrared. So we needed to get it out someplace where it was going to be very, very cold and we could maintain that almost 0 degree Kelvin temperature. And so ultimately what they settled on was L2, that they were going to park this at L2, which is beyond the orbit of the moon, far beyond Earth orbit, on the far side of the sun. And the Webb Space Telescope is actually technically in an orbit around L2. And I've done some research to try, I have not had a chance to actually ask a mission scientist. My understanding is that it takes less effort to maintain an orbit around the Lagrange point than it is to actually stay at the specific Lagrange point. So it's actually easier for the scientists and the engineers to maintain a tiny little orbit around the L2 spot than to actually just park it there and just leave it there. So that is actually where we targeted, and in fact where Webb is doing its science operations today. And so we knew that if this was going to be delivered to L2, that we needed to be able to get this where it was going to go, and it needed to be able to stay there and do everything, all science operations, after doing that very complicated 344 mission critical stop points, that it needed to be able to do that without any hope of a human serviceable mission to be able to go out there and take care of the mission. So the great news is the launch was incredibly successful, so successful that we used way less fuel getting to the L2 than we actually expected to, which is great for mission operations. It means it extends the life of the mission. It means we have more fuel available to continue operating Webb far beyond the initial, I believe it was a 10-year mission, but we predict now it will be well beyond 10 years we'll be able to operate it. So those are some of the considerations in actually constructing and deploying Webb. Now let's talk about some of the science. Like, what has Webb actually begun to surface for us, and what was it actually designed to do? There's really about 5 different areas of investigation that the Webb was designed to achieve. The first one is really to understand what we already talked about. What did the early universe look like? We want to understand the first stars that were formed, the first galaxies that were formed. We also want to understand a little bit more about the structure of galaxies. And we can, if we have a larger sample size of galaxies, we can better understand the formation of galaxies in general. Not just what they were like at the beginning of the universe, but how they evolve even today. And then specifically, we have interest in my experience, everybody's favorite topic, black holes. Black holes are like the Tyrannosaurus Rex of space science. Like, all kids want to talk about black holes. Everyone wants to talk about black holes. We also want to understand about the life cycle of stars, from their birth to their death, how they come to be, and how they continue to evolve. Planetary systems, I was just speaking with Don before, we'll be here on Thursday, that's next week. Right before this talk, we were talking about the exoplanets, the thousands of planets that we have discovered beyond our own solar system, and we've begun to understand a little bit more about the nature of those planets, again, thanks to investigations from James Webb Space Telescope, and that's where the study of exoplanets and atmospheres, not just planetary systems, but the exoplanets themselves as well. So, if I take each of these, so we start off with what the early universe looked like, after that. So this was actually this is actually among the first, I think there were 4 images that they released when the very first Webb Space Telescope images came out about 2 years ago now. This was from first light, and it's actually a series of stars and galaxies, some of which are very distant from us. Actually, if you notice, there's kind of, everybody see these kind of like streaky bits in here? There's like this guy here, these kind of like, they almost look like comets or something shooting across here. Does anybody know what those are?
Gravitational lensing.
Gravitational lensing. What's gravitational lensing?
It's gravity deflecting the satellite.
It is. It's gravity. So they call it gravitational lensing, and the reason they call it that is because as starlight from more distant objects passes objects that are closer to us, when those objects have expressed gravity on the light that is transmitted towards us, we experience the light as it passes by them as these bent bits of light. And what's useful about this phenomena is we can actually use it as a lens might be used. We can actually use gravity as a lens to observe objects that are more distant from us more effectively than we could if there wasn't an object between us and the object we were trying to observe. So this is about this galaxy collection is about 4.3 billion light years from Earth, and you can see that it has the effects of that gravitational lensing, which is even more helpful in us seeing these distant objects. This is actually just an image I wanted to show that compares. And again, there's been lots of comparisons between, well, Hubble was amazing, and it is amazing. It's still doing scientific operations today, and it's still an incredibly important scientific instrument. But yes, of course, the James Webb Space Telescope is capable of seeing better, it's got a bigger mirror, so it can see better than the Hubble, but it's not just about seeing better, it's about seeing different. And we talked about that when we talk about being able to observe in infrared. We literally can see things with the Webb Space Telescope that we cannot see with Hubble because it's tuned to see further into the infrared. Does anybody know, does anybody recognize, any movie buffs, does anybody recognize this television?
George Bailey.
George Bailey, yes! This is the beginning of It's a Wonderful, this is the beginning. It's a Wonderful Life. So this is actually a set of galaxies known as Stephan's Quintet. This was discovered all the way back in the 1800s, and it has long had a fascination for astronomers and for fans of Jimmy Stewart and Don Reed, and was used at the beginning of It's a Wonderful Life, and was one of the early objects that the Webb Space Telescope turned its sights toward. So this will give you a little bit of a sense of, as we use the different capabilities on Webb, how we're able to observe objects in different ways and learn different things about them based on how we observe them. So this was the Hubble camera. This is mostly invisible light of Stephan's Quintet, and it's mostly visible light with a little bit of infrared. The Hubble does have infrared capabilities, not as robust as the Webb Space Telescope. As you look here, this is actually now same object, same set of objects, viewed with another couple of the instruments that the Webb Space Telescope has, and you start to get a sense of, okay, you start to see different kinds of structures in here. You can start to see these are star-forming regions, and here, and here, and here. All of these parts of these galaxies are not really observable when we look at them using visible light or infrared. These are extremely interesting for what I just said about how galaxies and how black holes form, all of these areas in here. And then if we look at one more advancement here, now we're just using, so these are two different instruments with the output put together in order to comprise this image. This is just one of the Webb Space Telescope images, and you suddenly start to get a sense that you're almost like pulling away a whole bunch of things that were obscuring our ability to literally see these seemingly very bright, now that you're like really focused on infrared, these seemingly very bright areas of star formation and other events which are taking place primarily in infrared. And all of this other very, very interesting, very, very scientifically useful data that is now, we're removing that from the picture because we're no longer viewing in visible spectrum. We're now exclusively viewing in infrared. Let's see here. This one is really a little bit more about the life cycle of stars. I will play this video. This was before a lot of the more recent innovations, discoveries of James Webb. This was just theory.
The galaxy's most beautiful localities. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1 million years old. Hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope,
With
a mirror larger than Hubble.
So, which of course we now have. So this was one of the reasons why we wanted to be able to observe in infrared. We wanted to observe these stellar nurseries, the birth of these stars, these events which were previously obscure to us because of all the gas and visible light that was obscuring it. So this is an example of a star-forming region observed in visible light. And then when you look at it in infrared, you peel away all of those layers of gas and dust, and you start to actually be able to see these very specific star-forming, these nurseries, star-forming nurseries. This was also visible. This is actually also in the Horsehead Nebula in Orion. It gives you a sense of what that looks like in visible light using Hubble. And just the structures and the formation, literally, these are all stars down in here, this whole region, These stars here are stars that are likely between the nebula and us. These are stars that actually reside inside of the nebula. We were unable to see those before. Now when we begin to look at infrared, we can start to observe those stellar nurseries. This was, I just love this particular image. This is an image of, it's using one of the infrared instruments on James Webb Space Telescope. This is Rho Ophiuchi in Ophiuchus. But again, one of the reasons I think the Hubble was so successful in popularizing space science is because it just so happens that images that are very valuable to astronomers and scientists also happen to be just very beautiful. They have aesthetic beauty to them. And this particular star-forming region, this is about 400 light years distant from Earth. It's one of the closest star-forming regions to the Earth. And the stars, all these stars here, these are all brand new baby stars, that are just being unswaddled by the gases and the dust that they're being born inside of. And each of you can actually even start to see, like, there's even some structure in here around these stars. This is one of the exciting things about the life cycle of stars and the planetary formation around them. Those could very possibly begin to coalesce and to form planets around these stars, and we could actually potentially observe that, again, depending on how far, how distant, how well things have matured, and how far, depending on where we look, we have the opportunity to actually observe some of those phenomena and put some of those pieces together. And this is actually another image, again, from the Webb Space Telescope. This actually is blocked at the center here, a star. These are, we believe these are accretion disks. So these are actually the elements, the prototypical elements that are necessary in order for planets to begin to form around stars. And so we've known that in this case, AU microscopy has been surrounded by planet-forming disks. We were able to observe that by observing gravitational lensing, other evidence. But James Webb is actually beginning to give us the opportunity to image some of those things and to view them directly. And just because I was curious myself, the diagram that the Webb Space Telescope science team released showed us that this was 9.7 astronomical units. That's a distance. 1 astronomical unit is the average distance between the Earth and the Sun. So 9 of those would be roughly 9 times the distance of the Earth and the Sun. And so I just wanted to see, okay, so here's a star, here's this set of mass, this prototypical accretion disk, which we believe may be the beginning of planets, and I just took that and put it roughly on the same scale of our own solar system. So it looks roughly like this set of matter could give rise to maybe a set of planets that would resemble in some way our own solar system. So the point of this was just that this is roughly on the same scale as this accretion disk here. So then, so that's about the planetary, interest that the Webb Space Telescope lends the data to us better understanding the formation of planets and planetary systems. And then the fifth of those 5 scientific missions that Webb was really designed to address was studying exoplanets, their atmospheres, and the building blocks of life. As I mentioned, Kepler was a mission which preceded the James Webb Space Telescope. Its whole mission was basically to find exoplanets. Find planets that are beyond our own solar system, and there are multiple methods which are very innovative that we use to do that, but it basically was finding candidates for the Webb Space Telescope to then go back and to look at literally the atmosphere of these planets. So we can know a great deal just by observing stars and how the light dims and how they move. If a planet is tugging on them, we can know, without looking at their atmospheres, a little bit about their distance from the suns, and a little bit about the mass of those planets. So we can put those pieces together. Now, with the James Webb Space Telescope, what we're able to do is observe these stars that we now know from previous missions have planets going around them. And when this planet transits the star, when it passes in front of it, the spectra of the light changes to the instruments here on Earth. And when that happens, it gives us clues about the elements which are present in the atmosphere. I'm going to say that again because it's so cool I can barely believe it's true. They can look at stars, and they can observe the spectra of that star. And then when a planet passes in front of it, they observe the change in the spectra of the light, and from the spectra of the light, they can deduce the composition of the atmosphere of the planet. That, we are living in pretty amazing times. When you think about, we didn't even know that Saturn had rings like a few hundred years ago. We didn't know that Jupiter had moons. And now we are literally investigating planets which are hundreds and thousands of light years away from us, and we can try to piece together what the composition of the atmosphere is, perhaps in the interest of trying to determine which of those planets are capable of harboring life as we understand it can exist. That's pretty cool stuff. So this is an example of this particular, this is the WASP 39b exoplanet. And again, based on the spectra of the light that we see passing through this particular planet's atmosphere, we know what spectra carbon dioxide should have, those elements should have when we do spectroscopy on it. And we can deduce that there is a large presence of carbon dioxide in this particular atmosphere of this particular planet. And of course, we can use the James Webb Space Telescope to look at things in our own backyard. These are some of the highest resolution images. These are some of the first images of the rings of Neptune and Uranus that we've been able to see literally since Voyager passed by them like 30, 40 years ago. So what's the utility and the ability, the many different things that Webb can do, I would argue, yes, it was an expensive instrument. It is a staggering achievement of engineering, and it is an extraordinary scientific instrument which is just beginning to unlock some of these secrets for us. And I will just finish with a couple of things that Webb. So about a year ago, I gave this presentation, and it was, we had about at that point about a year worth of scientific evaluation. We've had a lot more since then. Webb is churning out so much data. What's amazing is a lot of this data is available to anybody who chooses to download it. Literally, you can download the raw material that Webb is putting out as a public resource. There are some things which we do not understand. There are many things which we are beginning to peel back with the Webb Space Telescope that don't really work with our current understanding, particularly of the early universe. So this is a particular image, as I mentioned, everybody loves black holes. This is a particular kind of black hole. This is a quasar, which is a ultra-luminous center of a galaxy. This is being powered by a supermassive black hole. The challenge that we currently have with this data is that we see early black holes that have only had a very short period of time to exist. And I was trying to see if I had included in my notes how old this particular supermassive black hole is. It's in the very early universe, within the first billion years, because I didn't mention this up to this point. Remember, light travels at a fixed speed. So as we look further and further away, we are seeing objects that are not only further from us, we are seeing objects as they existed long, long ago. And at some point, we reach a limit to how far back in time, space-time, we can actually look. Confusing concept, but just keep in mind, if the sun exploded at noon tomorrow, it would be 12:08 before we knew that the sun had exploded, because it would take that long for light to actually transmit to the Earth. The further away something is, the longer it takes light to get to us. And when we're looking at the beginning of the galaxies, at the beginning of the universe, the things we see are from a very, very long time ago. So we have this little conundrum here where we see early supermassive black holes which seem to have way more mass and are much more luminous than should have been possible for them to form and accrete as much mass as they seem to have. We do not have good explanations for this. We need to do more investigations. This is another conundrum that Webb has already begun to create for us, which is, as you saw, I don't know if you noticed, but especially in that video of the early universe from the Hubble, some of those galaxies were not necessarily very well formed. They didn't have a lot of structure to them. They kind of looked kind of blobby, they were kind of red and yellow and kind of all clumped together. We did not expect that we would see galaxies with a very strong amount of structure as we look back to the very beginning of the universe. That is not what we are beginning to see with the James Webb Space Telescope. So these galaxies that formed fewer than 6 billion years after the assumed and theoretical Big Bang. And we are seeing that there is a surprising amount of structure in these. We see that there is a surprising amount of spiral shape. We just did not expect to see matter accrete and form these kinds of shapes this early in the formation of the universe. Another mystery which Webb has created for us. Another one of the mysteries, this one is actually just at the, actually really is not a problem that Webb created, that the Webb created. There is a particular value which in science, in space science, astronomers and scientists are very interested in learning more about. This particular value is known as the Hubble constant. It would allow us to predict the rate at which things are flying apart from one another. It also would give rise to understanding of closed universe or an open universe and where the universe ultimately might go in its evolution. So we do not have any precise value for the Hubble constant. It would be great if we did, because it would allow us to predict the future of what the universe is likely to become. Webb Space Telescope has created more, it's given us a great deal of data. There is not only no conclusive answer to the Hubble constant, it actually has given us evidence which appears to be contradictory. But that's why we're doing science, so that we can try and understand these things. These mysteries are science working. These are the things we want to test our own theories and hypotheses around. And then this one is really, again, about galaxy formation. I mentioned that. Not only are we seeing galaxies in the early universe which have more structure, we're also seeing galaxies in the early universe which have more mass, more stuff inside of them than our theories would have predicted. So, as I say, these are all amazing mysteries which the Webb Space Telescope are informing with more data. We're learning more all the time. I think it's incredibly exciting and awesome that we actually live in a time where not only are we capable of asking these questions, but we're capable of beginning to get data, even if we don't know what to make of that data. Well, the answer to solving these mysteries is more data, and that's why, as I said, Webb will be operating for at least another 10 years, and we have the opportunity to live in a time where we can begin to ask these questions and to learn a little bit more. So with that, I will close with the video which was created for Webb's first anniversary.
Liftoff from a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe. Quite a Christmas present for the world's astronomers.
We're really just getting started on a lot of this. I will say just a couple quick more things, and then I'm happy to take as many questions as folks have. If you have interest in this, first of all, again, thank you to the South Shore Astronomical Society for lending telescopes that we hopefully have clear skies we can look through this evening. The Scituate Town Library actually lends out instruments. If there are folks here who don't own a telescope and you kind of are curious about it, you can borrow binoculars from them. They've got a telescope that's available to take out. All you need is a library card, and you can take out those instruments for yourselves. And then, of course, the map over to where we're going to join everybody, hopefully, with clear skies. And at least to climb the tower, which I'm looking forward to. So with that, I thank you guys all again for all of your attention, and I'm happy to take questions if you got them. They can orbit around black holes.
Yeah.
What?
Accretion.
Accretion disks. Absolutely. Yeah. I mean, accretion disks are just matter that are forming around some kind of a gravitational event. So absolutely, matter can form and shape around any kind of gravitational object. Absolutely. Question?
In layman's terms, can you describe how the scientists make the galaxies that they're looking at, that they think are maturely formed for their age?
So there may be others in this room who are, so I do know the mechanism by which they're able to do that, and it has to do with the phenomenon that we talked about, which was the shifting of light. So based on how much the light has shifted in an object, we can determine its distance from it. It's the redshift value of an object. The question I have always had, and perhaps someone can explain it better than I, that requires you to know the baseline of the spectra of the object that you're viewing. So if you know what the spectra should look like, and now you can observe it and you can see that it has shifted, you can evaluate that as a delta between this is what the spectra should look like, it is now shifted further into the red, and based on that, I can calculate its distance because it would have taken, the wavelengths have stretched that much further in the time it has taken light to reach me. The question that I have as an add to that is sort of like how they determine the baseline spectra. But that is the mechanism that they use. It's the redshift of an object which we use to determine its distance from us.
Do you also have to know the starting point?
You would need to know, that's what I was saying. So scientists know the starting point through mechanisms I can't explain. And then based on that, they're able to determine the redshift value as it has shifted further from its baseline spectra. So yes, that is how they're. And they have specific, I think it's a Z value is what it's called, but that's the value of the redshift directly informs our understanding of the distance of the object.
Why do the engineers use gold, golden, I don't know if you want to learn about it.
I believe it is actually gold, and so my understanding is, first of all, just its reflectivity. So it needs to be super efficient in being able to reflect specifically the infrared wavelengths that it's designed to reflect. But unfortunately, I don't know the material science behind it other than it's designed for longevity. So it needs to be able to not deteriorate or misshape in any way, that once they have formed those mirrors into their specific shapes, that's it, it's not going to change. And also that it's extremely efficient in reflecting the infrared. Oh, awesome. Fantastic. There's for those who are interested, there's a telescope right out front, right outside the door, which is fantastic. Did you have a comment or a question?
Do you have a feel for how many planets they've identified thus far that fall within the range of potentially supported?
So I was so ready to answer your first question that you changed me at the end. So I know that there are approximately 3,700 exoplanets which have been confirmed. Of those, there's a really, again, no affiliation, but there's a really cool app called Exoplanet, the original name, which it runs on iPhone, probably Android as well. And it actually represents visually not just the orbital motion of the planet around their host stars, but it also shows you for every star that has a planet or planet system around it where the so-called Goldilocks zone resides, which is what you're asking about. So I do not know of those 3,700 how many of them reside within that Goldilocks zone. So I can't answer that. Perhaps someone else.
How do they know there was a beginning to the universe?
That's a really good question.
Why would it just exist forever and ever and ever?
So, as I would explain it, it has to do with an accidental scientific experiment which took place in the 60s and 70s. So in the 60s and 70s, there were a pair of scientists who were working for Bell Labs who were actually trying to attenuate an antenna for a commercial purpose for Bell Labs. And they ended up getting this noise in the background, which they didn't have an explanation for. Many years later, and several Nobel Prizes, what we've come to understand is we can actually perceive through a variety of instruments the echo of the beginning of the universe, if you want the sound of the Big Bang. The reason it's not just that one event. We can only see so far back into the universe. The scientific experiment I just described was actually effectively the echo of this event which occurred everywhere. Absolutely, anywhere we look in the around the Earth, we can perceive this remnant background noise. And when we look into microwaves, we can actually cast our gaze back very, very far in space and time. I showed you some of those objects that are 10, 13 billion years from us. There's a limitation to that. And it's literally imperceptible beyond that because it is all effectively an opaque presence of what we've come to refer to as the cosmic microwave background, but it is literally just the microwave remnants of what happened at the beginning. I don't want to say never, but we cannot conceive of a theoretical means of looking back further past that point. And that there's a limitation to our own ability to perceive into that part of the universe, we believe, because the environment was so hot and so dense at that point that literally there's no means of actually seeing back into that part of the universe. So these various experiments together give us a good amount of evidence that there was something that began. We don't know what came before that, but we have very, very limited means of seeing beyond that, and all these different points give us a fair amount of confidence that that was an event which actually took place everywhere all at once, and represented effectively the formation of the universe. How's that? That was a big question. I'm happy to talk more about any of that. There's multiple talks available on that.
I'll say this in a macro way. Who decides what James Webb is going to do tomorrow?
Oh, yeah.
And/or is every day for the next 10 years already been planned and fought over by different space scientists?
It's a really great question. So there is an institute which runs the Webb and the Hubble as well, the Space Science Institute, Space Telescope Science Institute, based in Maryland, actually operates both the Webb Space Telescope and the Hubble Space Telescope. They're the ones ultimately who are the arbiters of where they're going to point it. But there are candidates, constantly they're constantly reevaluating them. And honestly, if there's interesting science that someone suggests, like a doctoral student decides that they want to go look at a particular object, and the board reviews that, and they decided that it would be more interesting to bump that sooner into the event, into the list of things that they're going to evaluate, they will absolutely do that, and they do that all the time. As I said, there actually is a website where you can view. I assume they're probably related. You can view the output from Webb. You can actually download literally the raw data. In fact, citizen scientists have done this. They've downloaded the data and done their own processing. A lot of the stuff that you see here was done by the Space Science Institute and others. But just as it is available to the public to download that data, I'm quite certain that if you had a fascinating object that you'd like to point at, you could put that for consideration in front of the Space Science Telescope Consortium.
So, the reason there's, this barrier where we can't see through is because that's where, the universe was, kind of formed, and that's the barrier to the external universe.
Yeah, it looks like it's, from our perspective, if we look out far enough, everywhere all at once. Yeah, absolutely.
Yeah, early on, it got hit by a micrometeoroid, and they were kind of freaked out that so soon when they launched it, that it could degrade because space is space and different stuff flies around. Is there any update since that first, on how long this will endure?
Yeah.
In the spot that it's in?
Yeah, so from everything that I understand, the assumption is that we will run out of fuel to operate Webb long before it has any sort of a micrometeoroid event. Obviously, there's only so much we can do. It's like weather; we can't predict all of that. But the expectation is that its lifespan will be limited by the amount of fuel that it has available to do
They
space.
had extra fuel because successful
Yeah.
launch, right?
It was extremely efficient. They really nailed it. So this part of the room is, I don't know if it's because I'm over here, but you guys are all quiet over there. Any questions on that side of the room? Awesome. Well, I'll hang around and I'm happy to answer questions afterwards if you want to come up and happy to say hello. Otherwise, we've got telescopes right outside here. Oh, we still have some goodies, tchotchkes in the back, stickers and other information about current missions, but otherwise,
Bob, you've got to take over to Lawson Tower.
and we'll be heading over to Lawson Tower.
Tower's open, he's able to go up.
Awesome. Thank you so much. Thanks again.
So, when you put the thing together,